Right now, 4 human beings are hurtling back toward Earth at thousands of miles per hour. They have just done something no human has done in 54 years. They flew behind the moon, not past it, not near it, behind it, to the place where Earth disappears entirely, where radio signals cannot reach and mission control goes completely silent, where whatever exists on the other side of that grey, ancient cratered surface is the only thing filling your window. And for approximately 40 minutes, those 4 astronauts were completely alone. No contact with Earth, no signal, no voice through the earpiece, no confirmation from anyone on the planet below that anything was okay. Just the far side of the moon, a solar eclipse unlike anything a human being has witnessed in all of recorded spaceflight history, and a series of sights that the crew, upon re-establishing contact, struggled to translate into language. Some of those sights have been explained. Some are being explained right now as this is recorded, and some, the ones the crew described in careful, precise, measured language during their first press conference after the flyby, do not yet have a complete scientific account. This is not speculation. This is not dramatization. This is not a conspiracy. This is what the data says. This is what the crew said, on the record in public to journalists and to mission controllers. This is what the science behind those moments actually tells us when you follow it carefully and honestly to the edges of what is currently confirmed. Before we go any further, and I want to say this genuinely, not as a formality, as always on this channel, the background footage is just space visuals running behind the words. It does not carry the story. The story lives entirely in what you hear, so close your eyes if that helps. Put the phone face down on the nightstand. Pull the blanket up. Let this be the thing your brain follows instead of everything else it wants to run in circles tonight. This was made for exactly that. For the quiet hours, for the listening, for the unhurried kind of understanding that only happens when you stop rushing toward the next thing. If this is the kind of investigation you want more of, subscribe now, because the investigation starts here, immediately, and it does not pause. To understand what Artemis II actually encountered, you need to understand what this mission was in precise terms, not the headline version, not the version that fits into a social media caption, the specific technical and historical reality of what was attempted and achieved, because that reality changes everything about how you hear what the crew described when they came back around the lunar limb and re-established contact with the rest of humanity. Artemis II launched on April 1st, 2026, from Launch Pad 39B at Kennedy Space Center in Florida. The launch time was 6:35 in the evening Eastern Time. 4 astronauts aboard a spacecraft called Orion sitting atop the Space Launch System, a vehicle that generates over 8 million pounds of thrust at liftoff, making it the most powerful rocket the United States has successfully flown in a generation. The Saturn V, which carried the Apollo missions to the Moon between 1967 and 1972, generated approximately 7.6 million pounds of thrust. The Space Launch System surpasses it. We're talking about a machine designed to do something no American crewed rocket has done in over 50 years, send human beings beyond low Earth orbit. The crew, Reed Wiseman, mission commander, a Navy test pilot, a graduate of the United States Naval Academy, a former International Space Station commander. He has logged over 165 days in space on 2 previous missions. He's the kind of person who, when asked how something felt, tends to pause, look for the precise word, and then use it carefully. We will return to that quality. Victor Glover, the pilot, naval aviator. The first black astronaut to serve as a long-duration crew member on the International Space Station, where he spent 168 days from November 2020 to May 2021. He is the person on this crew who, during the flyby, described what they saw with the most technical precision and the least ornamentation. His descriptions of the eclipse, of the surface, of the flashes, these are the descriptions that the science community is most closely passing. Christina Koch, mission specialist, an electrical engineer. She holds the record for the longest single spaceflight by a woman, 328 consecutive days on the International Space Station, from March 2019 to February 2020. She was, on Artemis II, the first woman to travel beyond low Earth orbit. That is not a minor distinction. The distinction matters historically. Every woman who goes to space from here forward builds on a record that was set here, on this mission, in this capsule. Jeremy Hansen, Mission Specialist, Canadian Space Agency, a former fighter pilot. He had been to the ISS before, he had experienced low Earth orbit, but he had never been beyond it. Artemis II made him the first Canadian in the entire history of human spaceflight to travel beyond Earth's orbit. Canada has contributed significantly to international spaceflight. The Canadarm robotic systems on the shuttle and the ISS, several Canadian astronauts with distinguished careers, but no Canadian had gone this far. Hansen went first. These 4 people, with between them hundreds of days in space, described the experience of the lunar flyby in ways that distinguished it sharply from everything they had done before. We will come to those descriptions. But first, the machinery of the mission, because the machinery is what made those descriptions possible. The heat shield issue deserves its own section. Not because it is a scandal or a cover-up, it is neither, but because it is the single most consequential unresolved technical question of the Artemis program, and understanding it changes how you read the courage required to get into this particular spacecraft on this particular mission. Orion re-enters Earth's atmosphere at approximately 25,000 miles per hour when returning from the Moon. That is the speed dictated by the trajectory. It is faster than a return from low Earth orbit, which is typically around 17,000 miles per hour. The difference is not trivial. Kinetic energy scales with the square of velocity, which means that going from 17,000 to 25,000 miles per hour approximately doubles the kinetic energy that the heat shield must absorb and dissipate. The heat shield is the entire reason anyone inside the capsule survives re-entry. It is not optional. It is not redundant. It is the single component whose failure is non-recoverable. The heat shield material is called AV coat. It is an ablative compound. It works by charring and vaporizing in a controlled way during re-entry, carrying heat away from the capsule structure before it can transfer into the vehicle and the crew. The vaporization is not a malfunction. It is the mechanism. The shield is designed to burn away. After Artemis I returned in December 2022, engineers inspecting the heat shield found that the AV coat had ablated differently than the pre-flight models predicted. Sections of the material had eroded more extensively than expected. The temperatures inside the crew module had stayed within acceptable limits. That is confirmed. The vehicle was not damaged in any way that would have endangered a crew. But the behavior of the material was not what the models said it would be. The models were wrong about something. In aerospace engineering, this kind of discrepancy is taken extremely seriously for a specific reason. If the model is wrong about how the material behaves, then the model cannot reliably predict what will happen on the next flight. The model needs to be corrected, or the margin for error needs to be understood with more precision before you put people inside the capsule and send it toward the Moon. NASA spent over a year analysing the data. They ran additional thermal tests. They commissioned independent reviews. They brought in external experts. Some of those experts, after reviewing the analysis, raised objections. They argued that the uncertainty in the model was not sufficiently resolved to justify crewed flight. They recommended waiting until a redesigned heat shield was ready. Other experts, and ultimately NASA leadership, reviewed the same data and reached a different conclusion. In January 2026, Administrator Jared Isaacman publicly stated that he had reviewed the engineering analysis and was satisfied that the existing heat shield provides sufficient margin for a crewed mission. He acknowledged the disagreement among reviewers. He acknowledged that design changes addressing the AV coat permeability behavior are planned for the Artemis III heat shield. He stated that the Artemis II mission would proceed. The crew was briefed. They are professional test pilots. Evaluating calculated risk and making informed decisions about whether to accept it is literally what test pilots do. They reviewed the engineering case. They accepted it. Whether the Artemis II heat shield performs as the models now predict during its actual crewed re-entry from lunar distance is a question that, as of this recording, does not yet have an answer. Splashdown is scheduled for April 10th. The re-entry data will be the most consequential technical result of the entire mission. It will either validate the engineering case or introduce new questions that will affect Artemis III's timeline and design. This is the background against which 4 people launched on April 1st. They knew about the heat shield analysis. They knew about the disagreement. They chose to go. The mission profile is called a free return trajectory. This is physics from the Apollo era. and it is worth explaining precisely because the specific mechanics of this trajectory type are what determined everything about the experience of this mission. The distance record, the flyby geometry, the blackout duration, and the way in which the crew came around the far side and saw the Earth again. A free return trajectory exploits the Moon's gravity as a passive redirect mechanism. The spacecraft travels from Earth to the Moon on a precisely calculated curved path, approaches the Moon, swings around the far side in a gravitational arc, and uses the Moon's gravity to redirect its velocity back toward Earth. No significant propulsion is required during the flyby itself. The Moon's gravity does the work. The spacecraft is a passenger. This is different from what the Apollo landing missions did. Missions from Apollo 11 onward, the ones that actually landed on the Moon, had to actively brake when they arrived. They fired their service propulsion engines to slow down enough to enter lunar orbit. That maneuver requires propellant, and significant propellant at that. It is what enabled them to orbit the Moon and then descend to the surface. But it is also a commitment. Once you burn to enter lunar orbit, you are in orbit, and you need another burn to leave. The free return trajectory bypasses this commitment entirely. You approach, you swing, you return. Apollo 13 demonstrated both the utility and the limits of this trajectory in April 1970. The mission had departed the free return trajectory in preparation for its planned lunar orbital insertion. When the oxygen tank exploded 55 hours and 55 minutes into the flight, the lunar landing was abandoned immediately. The crew needed to get home. The decision was made to fire the lunar module's descent engine to return to a free return trajectory, to use the Moon's gravity to redirect the spacecraft back toward Earth. An additional burn was made later to speed up the return. The combined effect of the trajectory correction and the free return arc pushed the crew to a maximum distance of approximately 248,655 miles from Earth. That was the record. It held for 56 years. Artemis II broke it on a planned mission in a functioning spacecraft with all systems nominal. The free return trajectory that takes you from Earth around the far side of the Moon and back requires passing farther from Earth than a trajectory designed to capture you in lunar orbit. This is geometry. The Artemis II crew reached 252,760 miles from Earth. That is approximately 4,105 miles beyond the Apollo 13 record, 252,760 miles. Let me translate that into something your brain can process with less abstraction. The distance from Earth to the Moon is, on average, approximately 238,855 miles. The Artemis II crew went significantly beyond the Moon. They were on the far side of the Moon and still moving away from Earth when they hit the maximum distance. Every person alive on this planet, every single one of the approximately 8 billion people, breathing, sleeping, working, arguing, making breakfast at the moment the Artemis II crew hit that distance, was closer to the planet those people came from than those 4 people were. The record is absolute. It is the farthest any human being has been from Earth since the species began. 4 days into the mission, 4 days of system evaluations, manual piloting tests, medical checks, exercise routines, private family calls over secure links, and looking out the windows as the Earth shrank from a planet into a circle, into a small luminous disk. Then, April 6th. The crew woke to a message from Jim Lovell. Jim Lovell died in 2025 at the age of 97. Before he died, he recorded a message specifically for the Artemis II crew, to be played on the day of the lunar flyby. Lovell had flown around the Moon twice, once on Apollo 8 in December 1968, the first crewed mission to leave Earth's orbit, and once on Apollo 13 in April 1970, the mission that nearly killed him. He knew what it was to fly around the far side and go silent. He knew what it was to emerge on the other side and see the Earth again. He recorded his message knowing he would not be alive to hear the response. "Welcome to my old neighbourhood," Lovell said. "When Frank Borman, Bill Anders and I orbited the Moon on Apollo 8, we got humanity's first up-close look at the Moon and got a view of the home planet that inspired and united people around the world. I'm proud to pass that torch on to you as you swing around the Moon. Don't forget to enjoy the view." Commander Wiseman, on the radio to Mission Control, called it an awesome message. The crew had science to do. The plan for the lunar flyby included direct observation of the lunar surface by the crew. photographic documentation, geological feature identification, visual reporting of specific targets listed in the mission science plan. This is not redundant to orbital imagery. It is worth explaining why. The human visual system processes spatial information in ways that current imaging technology does not fully replicate. Stereoscopic depth perception, the brain's ability to construct a three-dimensional model of a scene from the slightly different images received by the two eyes, allows trained observers to perceive topographic relief that is not clearly visible in flat photographic images taken from orbital altitude. Contrast sensitivity in varying illumination conditions allows the human eye to discern surface texture differences at the boundary between detection and non-detection. And perhaps most importantly, the human ability to notice anomalies, to perceive something that does not fit the expected pattern, is a capability that has no direct equivalent in automated image processing systems which are built to match patterns, not to notice when patterns are absent. The scientists who planned the Artemis II science activities specifically wanted human observers to look at the lunar surface because a trained human eye with access to decades of scientific context, the context that had been loaded into the crew's minds during mission briefings, might observe things that neither satellites nor algorithms would flag as significant. The crew had their instruments, their checklists, and their eyes. They had approximately 7 hours of close approach to work with. And they had one more thing, a celestial alignment that no crew in the history of spaceflight had encountered in quite this configuration. The eclipse. Let us be precise about what a solar eclipse is and why the one the Artemis II crew experienced was categorically different from any eclipse in the observational history of this phenomenon. A solar eclipse occurs when the moon passes between a viewer and the sun, blocking the sun's light. From Earth's surface, total solar eclipses last at most approximately 7 minutes and 32 seconds at any given location. The path of totality, the corridor where the eclipse is total, sweeps across the planet at roughly 1,500 km per hour. Any fixed point on the surface is in totality briefly. The geometry that makes total solar eclipses from Earth possible is, as many astronomers have noted, one of the most striking quantitative coincidences in the solar system. The Sun is approximately 400 times the diameter of the Moon. The Sun is approximately 400 times farther from Earth than the Moon. These two ratios cancel out almost exactly, producing near-identical apparent diameters for the two bodies as seen from Earth's surface. The match is close enough to produce totality. It is not perfect, both orbits are elliptical, so the apparent sizes vary slightly, which is why some alignments produce annular eclipses with a ring of sunlight around the Moon's edge rather than full totality. But the basic geometry is there. Now consider what happens when the observer is not on Earth but near the Moon. From the Orion spacecraft's position, at roughly 4,000 miles from the lunar surface, the Moon's apparent diameter was significantly larger than the Sun's, not approximately the same, noticeably larger. The 400 times distance ratio that produces size equality from Earth's surface no longer applies when you are close to the Moon. From Orion's position, the Moon's disk covered the solar disk completely and extended well beyond its edges on all sides. The result was totality lasting approximately 1 hour, 60 minutes. An hour of the Sun's outer atmosphere, the corona, visible as a halo around the black disk of the Moon. An hour of light levels comparable to deep twilight, illuminated only by the corona, by reflected sunlight from nearby surfaces, and by the earthshine falling on the lunar near side. An hour of the Sun's photosphere completely hidden. The corona is plasma, ionized gas, structured and shaped by the Sun's magnetic field into patterns that are invisible under normal conditions because the photosphere's brightness overwhelms everything nearby. Coronal streamers extend outward from the solar equator, following magnetic field lines for millions of kilometers into the heliosphere. Coronal holes, regions where the magnetic field opens outward into space and solar wind escapes at high velocity, appear as darker regions in the corona. The exact structure of the corona changes over the solar cycle. In 2026, the Sun is near solar maximum, the peak of its 11-year activity cycle. The corona is at its most complex and extensive. Victor Glover described the eclipse on the public affairs broadcast. He reported that the Sun had gone behind the Moon, that the corona was still visible, bright, creating what he called a halo under almost the entire lunar disk, that the Moon appeared as a black orb, his exact word, suspended in front of them, that the corona was bright enough to provide general illumination in the spacecraft, that he could see stars and planets. He specifically identified Venus, positioned near the moon's edge, visible because the eclipse had darkened the sky enough to reveal it. He mentioned that Mercury, Mars and Saturn were also potentially visible. This is confirmed. This is what was said on a live public broadcast to Mission Control, journalists and viewers worldwide. Now here is what is still being analysed. During the eclipse, during the 1-hour totality period, Glover reported that the crew observed flashes of light on the darkened lunar surface. Multiple flashes, brief, bright, distributed across different areas of the near-side surface that was now facing them in darkness. He described these carefully, not as anomalies, not as unexplainable. He described them as transient light events on the lunar surface. His phrasing was precise. He was not sensationalizing, he was reporting. The scientific term for what he was describing is transient lunar phenomena. They are real. This is established. They have been observed and recorded for centuries. Systematic observation programs designed specifically to detect lunar impact flashes began to develop serious scientific rigor in the late 20th century. The Lunar Meteoritic Impact Search Program, run from the Marshall Space Flight Center, began monitoring in 2006. It has detected and catalogued hundreds of confirmed impact events. The NELIOTA program, a joint project of the European Space Agency and the National Observatory of Athens, has been monitoring the lunar dark side using a dedicated 1.2-metre telescope at Cryonerion Station in Greece since 2017. The NELIOTA dataset, as of recent reporting, includes several hundred confirmed impact flash detections, complete with brightness measurements, colour measurements, and timing data. The rate of impact detections in these programs, combined with models of the small body population in near-Earth space, provides quantitative constraints on the meteoroid flux environment. This has practical implications for the design of future lunar surface infrastructure, habitats, power systems, scientific instruments, that will need to withstand meteoroid bombardment over operational lifetimes of years or decades. What the Artemis II crew observed is physically different from any ground-based detection of this phenomenon for reasons that are worth spelling out carefully. Ground-based programs observe flashes on the shadowed portions of the lunar near side, areas in darkness during the crescent phases. You need a dark surface to see a flash against it. This limits ground-based monitoring to specific portions of the lunar surface during specific phases. Roughly speaking, the complete near side is observable as a dark surface only twice per lunar month, during the first and last crescent phases, and each observing window is constrained by moonset and moonrise times and by atmospheric conditions. The Artemis II crew, during the hour of totality, had a completely different geometry. The entire near-side surface, the hemisphere that always faces Earth, was facing Orion and was in near-total darkness. The sun was blocked. The near side was illuminated only by the corona and by Earthshine. The crew was approximately 4,000 miles from the surface. No atmosphere between their eyes and the surface. No light pollution. No telescope optics introducing image processing artifacts or readout noise. Their visual system was dark adapted. The eclipse had been running for long enough that their pupils had dilated fully. The human eye in dark adapted conditions has extraordinary sensitivity to transient light events. Flashes, sparks, brief illuminations. The rod photoreceptors that dominate peripheral vision in low light are specifically sensitive to motion and change, not to static patterns. A brief flash on a dark surface would have been well within the detection capability of the crew's dark-adapted vision from that distance. Glover's report of multiple flashes, distributed across different regions of the near-side surface, was transmitted to Mission Control and recorded in the mission log. NASA scientists said after the flyby that these observations are being analysed in context of the existing transient lunar phenomena literature. The results of that analysis are not yet published. What we know in advance is this: if the crew's observations are consistent with impact events, they will provide a point of calibration for ground-based monitoring programs from a novel observation geometry. If the distribution of observed flashes reveals any spatial pattern, clustering in certain regions, correlation with known surface features, that would be new information about the geographic distribution of impact events, which is currently not well constrained because ground-based programs observe the Moon from a fixed geometry. and if any of the observed flashes are inconsistent with the impact model in their timing, brightness, or distribution, that inconsistency will need to be explained. This is established science in progress. This is not mystery. This is how new data enters a field. Now, the far side. To understand the scientific significance of what the crew observed and photographed as Orion flew around the far side of the moon, you need to understand what kind of place it is and why it is different from everything humanity has been able to observe from Earth. The moon is tidally locked to Earth. Tidal locking is the end state of a gravitational dissipation process that took hundreds of millions of years. The moon rotates on its own axis once every 27.3 days. It orbits Earth once every 27.3 days. The synchronization is not coincidental. It is the inevitable outcome of the gradual slowing of the moon's rotation by tidal friction, the slight differential gravitational pull that Earth exerts on the near side of the moon compared to the far side, which over time has braked the moon's spin to match its orbital period. The result is that every human being who has ever existed has seen the same face of the moon. Every calendar, every myth, every tidal table, every night anyone has looked up at a full moon. They were all looking at the same hemisphere. The other hemisphere was unknown until 1959. What the Lunar 3 photographs revealed, however imperfectly, was that the far side is fundamentally different from the near side. The near side has dark plains, the Maria, covering roughly 30% of its surface. The far side has almost none. The far side is highlands, ancient battered cratered highlands, showing a geological history that was apparently not disrupted by the volcanic activity that resurfaced the near side between 3 and 4 billion years ago. The cause of this asymmetry is one of the most discussed problems in lunar science. The leading current model involves crustal thickness. The far side crust is thicker. A thicker crust is harder to breach by volcanic activity. Magma rising from the interior finds it easier to reach the surface through a thinner crust, so the near side was more extensively resurfaced. The crustal thickness difference itself is explained, in most models, by the thermal history of the early moon. The near side, facing the warm young Earth, cooled more slowly and developed a less dense crust. This model has supporting evidence from orbital geochemical data but is not fully confirmed. A competing model, published in 2011 and still active in the literature, proposes that a small companion body formed alongside the moon in the original giant impact event that created the moon itself, and that this companion eventually collided with the far side in a slow accretion event, piling extra crustal material onto the far hemisphere and suppressing subsequent volcanic activity. The observational predictions of this model overlap with those of the simpler thermal model in some areas and differ in others. Distinguishing between them requires the kind of surface geochemical data that robotic and eventually crewed missions to the far side will provide. The Artemis II crew flew over this ancient terrain at roughly 4,000 miles altitude, with human eyes and cameras looking at features that no person had observed directly since the Apollo 17 crew flew around the near side limb in December 1972, and that no crew had observed from the flyby geometry of Artemis II ever. The Oriental Basin, located near the western limb of the near side but primarily resolvable from the far side, approximately 930 kilometers in diameter. Formation age approximately 3.8 to 3.9 billion years, placing it at the tail end of the late heavy bombardment, the period of elevated impact flux in the early inner solar system that scarred the surfaces of the Moon, Mars, Mercury, and the Earth's continental shields. Multi-ring impact basins form when a very large impacting body, typically an asteroid hundreds of kilometers in size, strikes a planetary surface and releases energy on a scale that exceeds the structural strength of the crust over a wide area. The compressed rock rebounds outward in concentric rings of uplifted terrain, like the rings formed when a stone hits a still pond but frozen in rock at the scale of hundreds of kilometers. In Orientale, the ring structure is among the best preserved in the solar system. The outermost ring, the Cordillera Mountains, stands as high as 7 kilometers above the basin floor. Interior to it, the Rook Mountains form an inner ring. The basin floor interior to the Rooks is relatively flat, flooded by a thin layer of impact melt that cooled in place after the collision. No human being had ever seen Oriental directly, with their own eyes, from a spacecraft, in person. Orbital imagery exists in high resolution. The Lunar Reconnaissance Orbiter has mapped Oriental at sufficient resolution to identify individual boulders. Three-dimensional terrain models derived from laser altimetry exist. Scientists have studied this basin extensively and know it in the data sense very well. What the crew saw was Oriental in physical space, in the specific illumination geometry of April 6, 2026, from a distance of approximately 4,000 miles at the exact subsolar latitude produced by that date and that trajectory. Orbital satellites pass over terrain at many different sun angles over many orbital cycles, but the combination of distance, phase angle, subsolar latitude and approach geometry present during the Artemis II flyby is unique to this mission. The images produced a new data. NASA confirmed after the flyby that the Artemis II crew was the first to directly observe the Oriental Basin. That statement is on the record. The South Pole Aitken Basin, the largest confirmed impact structure in the solar system. Let that land for a moment. Not the largest on the Moon, not the largest in the inner solar system, the largest known in the entire solar system, 2,500 kilometers across, 8 kilometers deep. If it were centered over the continental United States, it would cover the country entirely and extend into both oceans. The asteroid that formed it was large enough and moving fast enough to punch through the entire lunar crust and into the upper mantle, exposing material from the Moon's interior on the basin floor and in the surrounding ejecta deposits. The scientific significance of this is specifically about access. The lunar mantle has never been directly sampled. Apollo returned crustal samples. Robotic landers have collected crustal material. The interior of the Moon below the crust is known only indirectly, from Apollo seismic data and from orbital geochemical mapping. Direct physical access to mantle material would represent one of the most significant advances in planetary science of the current generation. The South Pole Aitken Basin is where that access exists. The impact exposed upper mantle material and scattered it across the basin floor and surrounding terrain. Future missions, crewed and robotics to the lunar South Polar region, adjacent to and inside the South Pole Aitken Basin, are specifically prioritized to collect this material and return it to Earth for analysis. Artemis III, currently planned to land near the lunar South Pole, will be the first attempt to collect samples from this region. What those samples contain will directly test models of the Moon's formation and internal structure, but the planning of Artemis III, the specific landing sites, the target formations, the routes for surface traverses, will be informed in part by the observational data from Artemis II. The crew observed the eastern rim of the basin during the flyby, not the centre. The trajectory took them over the rim terrain, not the basin floor. But rim terrain at this lighting, from this distance, in this geometry, is new data. It is in processing. The Vavilov crater, 98 kilometers in diameter, located on the rim of the Hertzsprung Basin, a 570-kilometer impact structure that predates it. The Hertzsprung Basin is ancient, formed during the late heavy bombardment. Vavilov formed into its rim later, a crater inside a crater, which is a common pattern in the heavily bombarded farside terrain. Vavilov's floor is anomalously smooth. This is the specific thing that lunar scientists are interested in from the Artemis II photographic data. Craters of Vavilov's age and size in the farside highlands typically have rough floors. Billions of years of smaller impacts disturb the surface. Mass wasting of the interior crater walls, rock sliding down slopes under the weak but persistent lunar gravity, deposits debris on the crater floor and disrupts it. Electrostatic and micrometeorite processes redistribute fine-grained regolith. The cumulative result is topographic roughness. Vavilov's floor does not look like this. It is flat, smooth. The contrast with the surrounding terrain is visible in orbital imagery. The most probable explanation is volcanic resurfacing. At some point after the Vavilov impact, magmatic material from the lunar interior entered the crater, perhaps through fractures in the floor opened by the impact itself, which would have weakened the crust at that location and flooded the basin. As the lava cooled, it produced a flat basaltic surface that has been less disrupted than the surrounding highlands because it was in place more recently and is therefore younger. This would make Vavilov a farside mare deposit, a small isolated pocket of volcanic infilling that is geologically related to the extensive nearside Maria, but is unusual and poorly understood in the farside context. Identifying and characterizing such deposits is important for understanding how long the lunar interior remained thermally active and where volcanic activity occurred on the far side during the Moon's geological history. The competing explanation is impact melt. The original Vavilov impact released enough energy to melt target rock over a significant area. If that melted rock pooled on the crater floor and solidified, it would produce a similarly smooth surface. Impact melt and volcanic basalt have different compositions and different photometric properties. They reflect light differently at different wavelengths and different phase angles, but distinguishing between them requires photometric data at specific geometries that existing orbital datasets have not fully provided for Vavilov. The Artemis II crew photographed Vavilov at a sun angle, and phase geometry that orbital passes have not replicated. Whether the resulting images provide the photometric information needed to discriminate between the volcanic and impact melt hypotheses is what the lunar science team is currently assessing. The analysis is ongoing. There is something worth saying about the specific nature of the far side terrain that the crew flew over, beyond the individual features. The far side of the Moon is, in a geological sense, the oldest accessible surface in the inner solar system. Earth's surface is geologically young. The planet is approximately 4.5 billion years old, but the oldest exposed surface rocks on Earth date to about 4 billion years ago, and vast areas of the continental surface are far younger than that, having been recycled by plate tectonics, reshaped by erosion, buried and exhumed over geological time. The oldest terrains on Earth have been chemically altered, metamorphosed, and restructured so extensively that they carry relatively little information about the early solar system. The far side of the Moon is different. The lunar far side highlands are estimated to be approximately 4.4 billion years old in large areas, older than anything intact on Earth's surface. They formed in the aftermath of the giant impact that created the Moon from proto-Earth debris, solidified during the rapid cooling of the lunar magma ocean, and have been preserved since then in a state of cold, geologically inactive stasis. The craters that have accumulated on them over 4.4 billion years are not scars on an evolving surface. They are a record, a continuous impact record stretching from the very early solar system to the present. Reading that record tells you about the history of the small body population in the inner solar system, the asteroids and comets that have passed through the vicinity of Earth and the Moon over billions of years. The density of craters on a surface is a clock. More craters means older surface. Less craters means the surface was either recently formed or recently resurfaced. The spatial distribution of craters, their sizes, their depths, their states of preservation, encodes information about the impactor population at different times in the solar system's history. The late heavy bombardment, referenced earlier in the context of Oriental's formation, is an event recorded in this crater record. It is a period approximately 3.8 to 4.1 billion years ago, during which the rate of large impacts appears to have been elevated relative to what came before and after. The evidence for it comes primarily from the ages of large lunar impact basins, multiple basins of similar age, clustered in a geological window suggesting a brief but intense period of bombardment. The cause is debated. One hypothesis invokes a gravitational resonance between Jupiter and Saturn that destabilized a population of asteroids and comets and sent them into the inner solar system. Another suggests the evidence is an artifact of sampling bias, since most of what we have sampled from the Moon are the ejecta of the large basin-forming impacts, which would naturally cluster near their formation ages regardless of what was happening at other times. The Artemis II crew flew over terrain that carries this record. They photographed it. Their visual observations of specific features, shadow geometries, rim morphologies, floor textures, will be compared against existing crater databases and against the models of impact history that planetary scientists use to interpret the far-side terrain. The results will not resolve the late heavy bombardment debate on their own, but they will contribute to the dataset. There is one more aspect of the far side that deserves mention: its unique radio-quiet environment. The Earth is a prolific emitter of radio waves. Artificial radio frequency signals, from broadcasting, telecommunications, radar, satellite communications, saturate the near-Earth electromagnetic environment across a wide range of frequencies. This electromagnetic pollution is a significant problem for radio astronomy, which attempts to detect extremely faint signals from astronomical sources at distances of millions or billions of light years. Radio telescopes on Earth are built as far as possible from population centres, in remote terrain, in protected radio-quiet zones, and they still struggle with interference. The far side of the Moon is perpetually shielded from Earth's radio emissions by the bulk of the lunar body. 300 meters of rock is sufficient to attenuate radio signals to negligible levels across nearly all frequencies. From the far side, the electromagnetic background from Earth is essentially zero. It is the quietest radio environment in the inner solar system. This makes the far side potentially the best location in the inner solar system for radio astronomy at long wavelengths, frequencies below roughly 30 MHz that cannot penetrate Earth's ionosphere, and that, above the ionosphere, are drowned in artificial interference. Astronomy at these wavelengths could in principle detect signatures of the early universe from the epoch before the first stars formed, a period called the Cosmic Dark Ages, when the universe was filled with neutral hydrogen and had not yet produced any sources of light. The hydrogen spin-flip transition, which produces radiation at 21 centimeters, would have been redshifted to long wavelengths by the expansion of the universe over billions of years. A radio telescope on the far side of the Moon could in principle detect this signal. No telescope in any other accessible location can. Several proposals for far-side lunar radio telescopes exist in the literature and in NASA planning documents. The Lunar Crater Radio Telescope concept, proposed as a potential deployment in a suitable crater on the far side, has been in NASA development studies. It would use a wire mesh deployed across a crater floor to form a large aperture receiving surface. The resulting telescope would be unlike any radio observatory currently in operation. The crew of Artemis II flew over the kind of terrain where such a telescope might one day be built. They looked at craters whose floors, smooth, protected in permanent radio silence, represent potential sites for instruments that could look back to the beginning of the universe. Koch mentioned this in her post-flyby statement. "We will do radio astronomy from the far side," she said. It was not an abstraction. It was a description of a specific scientific capability that the far side uniquely provides, and that is being actively planned. We should also talk about what the crew were not the first to see. The far side of the Moon has been imaged extensively by robotic spacecraft. This is important to say clearly, because the significance of the Artemis II crew's observations is not that the far side was previously unknown. It was not. It is that direct human observation provides something that robotic imagery does not, and understanding what that something is requires being precise about what robots can and cannot do. The Lunar Reconnaissance Orbiter has been in continuous operation around the Moon since June 2009. It carries a suite of instruments including the Lunar Reconnaissance Orbiter camera, which has imaged the entire lunar surface at a resolution sufficient to identify features approximately 50 centimeters across. At that resolution, individual boulders, small craters, surface irregularities of all kinds are visible. The camera has returned over 1 million images. The data volume is enormous. The Lunar Orbiter program in the 1960s imaged the Moon to support Apollo landing site selection. The Kaguya spacecraft, a Japanese mission that operated from 2007 to 2009, carried a terrain camera and produced high-resolution stereo imagery of the entire surface. The Clementine mission in 1994 produced a global map. The Grail mission in 2011 and 2012 produced a high-resolution gravity map. The SLEEN 2, Chandrayaan and Changi programs have added additional datasets. The Moon is the most comprehensively remotely sensed body in the solar system after the Earth. Its surface is mapped. Its gravity field is known. Its elemental composition has been characterized from orbit. Its topography has been measured to sub-meter vertical precision over much of the surface. What orbital mapping cannot do is what the Artemis II crew did on April 6th. Orbital passes are constrained to fixed geometries by the mechanics of orbit. A given orbital altitude and inclination produces a specific set of sun angles and phase angles at each ground track. You can choose an orbit to optimize for particular illumination conditions, but you cannot freely choose the observation geometry the way a spacecraft on a free return trajectory can, approaching at a specific angle, at a specific phase in the Moon's cycle relative to the Sun, from a specific direction. The Artemis II flyby took place on April 6, 2026. The Sun angle on the lunar surface at that date, from that approach direction, produced specific shadow patterns that highlighted specific topographic features. That illumination geometry is unique to this mission at this time, Future missions at different times will produce different illumination geometries. The data from April 6th is specific to April 6th. More importantly, and this is the part that is hardest to quantify, the crew brought something to the observation that no robotic system brings: context. The crew had been briefed extensively by lunar scientists before the mission. They knew what specific features to look for. They understood what questions the science community was trying to answer. They had internalized enough of the scientific context that their attention was directed, not diffuse. A trained human observer, looking at the lunar surface from 4,000 miles with a specific set of questions in mind, processes what they see differently from a camera pointed at the surface and triggered by a pre-programmed schedule. This is not an argument against robotic exploration. Robotic missions have done and will continue to do things that crewed missions cannot. They can operate for years in environments too hostile for human survival. They can be lost without catastrophe. They can carry instruments with sensitivity that exceeds human sensory capability by orders of magnitude. The case for robotic exploration is strong and well established. But the case for human observation is also real, and the Artemis II crew's flyby was, among other things, a test of it. Whether their observations reveal things that orbital imagery did not is a question that the data analysis will begin to answer over the coming months. There is one more piece of context that belongs in this investigation, and it concerns what comes next. Artemis II is not the end. It is the second mission in a program that is designed to return human beings to the lunar surface for the first time in over 50 years, establish a sustained human presence there, and use the moon as a proving ground for the technologies and techniques that will eventually support human missions to Mars. Artemis III is the next mission in the sequence. It is planned to land on the lunar surface, near the South Pole, in a region of permanently shadowed craters where water ice has been confirmed to exist by orbital measurements. The water ice is not a geological curiosity, it is a resource. Water can be electrolyzed into hydrogen and oxygen, which are rocket propellants. If water ice in sufficient quantities exists on the lunar surface in accessible locations, it represents the foundation of an in-situ resource utilization architecture that could make deep space exploration dramatically more affordable than it would otherwise be, because you would not have to lift propellant from Earth's surface gravity well, which is the most expensive part of deep space travel. The permanent shadow of the lunar south polar craters exists because the moon's axial tilt is only 1.5 degrees relative to the ecliptic, compared to Earth's 23.5 degrees. With so little tilt, the polar regions receive sunlight at a very low angle, and the floors of deep craters near the poles receive no sunlight at all, for billions of years. The temperature in these permanently shadowed regions is estimated at below -200 degrees Celsius. They are among the coldest places in the solar system. Any water ice that arrived there, from cometary impacts, from asteroid impacts, from the solar wind interacting with surface minerals, has been frozen in place ever since. The LCROSS mission in 2009 confirmed the presence of water ice at the South Pole by deliberately impacting the Cabeus crater and analysing the debris plume with the following spacecraft. Multiple orbital measurements since then have refined the estimate of ice distribution and concentration. The exact quantities accessible at specific locations are still being mapped. Artemis III will land near this ice. The crew will collect samples from the regolith, including from the edges of permanently shadowed regions. They will bring back material that has been preserved at those extreme temperatures for billions of years, material that may contain not just water ice but other volatile compounds. Carbon dioxide, carbon monoxide, methane, ammonia, all of which have been detected in the LCROSS plume. The organic chemistry of these deposits, analysed in Earth laboratories, will tell scientists something about the delivery of volatile compounds to the early inner solar system. The Artemis II flyby was a necessary precursor to Artemis III, not just technically, validating the Orion spacecraft, the SLS rocket, the life support systems, but scientifically. The crew's observations of the South Polar terrain during their flyby, from a different viewing geometry than orbital satellites provide, may contribute to the selection of the final landing site and the planning of surface traverses. Beyond Artemis III, the Gateway Lunar Orbital Station is in planning and partially in construction, an outpost in cislunar space, in a near rectilinear halo orbit around the Moon, that will serve as a staging point for surface missions and as a platform for scientific instruments. The Lunar Surface Innovation Initiative is developing technologies for power generation, thermal management, and excavation on the lunar surface. The Commercial Lunar Payload Services program is sending robotic landers to the Moon to characterize specific surface locations in advance of crewed missions. The program is large. It involves multiple agencies, multiple nations, multiple commercial partners. It has been delayed multiple times. It has faced budget uncertainty and political transitions, but it is real, it is funded, and it is in progress. What the Artemis II crew saw behind the Moon was a preview of a region that human beings are going to spend the next several decades learning, slowly, carefully, with instruments first and then with feet. The far side, those ancient highlands, those enormous basins, those anomalously smooth crater floors, is on the agenda, not immediately, but it is on the agenda. The Chinese Chang'e program has already landed on the far side. Chang'e 4 touched down in the Vonkaman crater, inside the South Pole Aitken Basin, in January 2019. It was the first soft landing on the far side in human spaceflight history. The Chang'e 4 rover, Yutu-2, has been operating on the far side surface since then, and has been returning data about the regolith composition and subsurface structure. China is planning additional far side missions. The far side of the Moon is not permanently out of reach. It is in the queue. And what the Artemis II crew photographed and observed during their flyby is part of the growing body of knowledge that will eventually guide where humans stand next. Now let us go back to the moment the signal came back. The free return trajectory brings the spacecraft around the far side of the Moon and back toward Earth. As Orion came around the lunar limb on the eastern side, the line of sight to Earth receivers was progressively restored. Mission Control confirmed signal acquisition. The 40-minute blackout ended, and simultaneously Earth appeared in the crew's windows, Earthrise. In December 1968, the Apollo 8 crew, Frank Borman, Jim Lovell, Bill Anders, were the first human beings to travel to the vicinity of the Moon. They orbited it 10 times. On one of those orbital passes, as their command module rotated, Earth appeared above the lunar horizon. Anders grabbed a camera loaded with colour film and took a photograph. That image, called Earthrise, became one of the most reproduced photographs in human history. A blue and white crescent Earth rising above the grey, lifeless lunar surface, seen for the first time by the first human beings to have gotten far enough from the planet to see it as an object. The cultural impact of that photograph is documented and real. Environmental historian Robert Poole argued in his 2008 book Earthrise that it contributed directly to the founding of Earth Day in 1970, to the Clean Water Act of 1972, to the formation of the Environmental Protection Agency, to the broad shift in public consciousness about the finite and fragile nature of the planet. Those arguments about causation are contested at the margins. The cultural impact itself is not contested. That photograph changed something. The Artemis II crew saw their own Earthrise after 40 minutes of the far side below them and no Earth visible anywhere. After an hour of solar corona, after the eclipse and the flashes and the cookies and the silence, Earth appeared at the edge of the lunar limb. Christina Koch spoke about this. In the post-flyby public affairs event, she said that looking at Earth from that position, and in that context, after having been cut off from it entirely, after having seen it from farther away than any living person, produced a feeling that she described as difficult to separate from a kind of grief. Not loss, she was careful to say, not regret. Something closer to the feeling you get when something very precious is very far away and you are responsible for returning to it. She said it made her understand, in a way that previous spaceflight had not, why the Apollo astronauts came back changed, why they spoke about the planet differently, why Edgar Mitchell, the Apollo 14 astronaut who walked on the lunar surface and looked up at the Earth, described what he called an instant global consciousness, a perception that the separation between himself and everything else was somehow artificial. Why almost every astronaut who has commented publicly on the experience of seeing Earth from space has said, in some form, that it is something language reaches for but cannot fully contain, the overview effect. Frank White's term, coined in 1987 after a series of interviews with astronauts who had experienced this shift. The consistent core of the reports, a visceral, sudden, not quite intellectual perception of the Earth as a unified system, a perception of the arbitrariness of the political, ethnic and cultural boundaries drawn across its surface, a perception of the planet as precious in a way that is immediate and physical rather than abstract and philosophical. The effect appears to scale with distance. ISS astronauts at 250 miles report it. Lunar orbit astronauts at 250,000 miles reported it more profoundly. The physics of perspective support this. The farther you are from a thing, the more completely it becomes a single object in your visual field, undifferentiated, whole. Koch's speech at the end of the flyby press event was measured and not theatrical. She did not perform emotion. She described what she experienced. She said, "We will explore, we will build, we will return to the moon, we will construct science outposts, we will do radio astronomy from the far side where Earth's electromagnetic noise cannot reach, we will drive rovers, we will found industries, we will be back, but ultimately," she said, "we will always choose Earth, we will always choose each other." That speech was heard live by mission controllers and by the public. It is documented. And Wiseman spent most of the post-flyby press event being precise. He described specific maneuvers, he described what the instruments showed, he talked about the system evaluations. He talked about how the mission was performing against its objectives. He was doing what a mission commander does, giving an account of the operation. And then someone asked him how it felt. He paused. Not a polite pause, not the kind of pause a person makes when they are choosing from several prepared answers. The kind of pause you see when someone is genuinely searching for language to describe something that language is not quite shaped for. He said that on the International Space Station, you are 250 nautical miles above the Earth. You are close enough that the planet fills a significant portion of your visual field. You can see weather systems, coastlines, the curvature of the atmosphere at the Terminator. You feel, he said feel, not think. You feel that you are still part of it, that the planet is still the context you exist within. From 250,000 miles, Earth is a disk, a small circle of blue and white against an absolute darkness, and the distances on the instruments, 252,000 miles, 248,000 miles. He said that as a human being you cannot actually process those numbers. You can read them, you can recite them, but the human brain does not have a sensory referent for that scale. You intellectually know the distance, but you do not feel it in the way you feel the distance from the ISS to Earth. Except, he said when Mission Control reoriented the spacecraft as the sun was setting behind the Earth, early in the mission, he did not know what to expect to see. And then he saw something, and he stopped there in the press conference searching for the word. Something he could not find language for. Something that had left the whole crew speechless. He called it the most complete thing he had ever experienced. Not the most beautiful, not the most terrifying, not the most significant or the most memorable, the most complete. That word is specific. It is not decoration. Completeness, in the sense he was using it, means something like this: a state that requires nothing added to it, an experience that is sufficient in itself, that contains within itself everything it needs. A moment where there is no gap between the experience and its meaning, where the experience is the meaning, without requiring any further explanation or context or translation. This is not the language of press releases. It is the language of a person who encountered something and has not yet finished understanding it. The blackout itself. Let us account for those 40 minutes more carefully, because the physical silence of the blackout is one thing, and the human experience of it is another, and both things matter to understanding this mission. The crew had a checklist for the blackout. They had science objectives. The 40-minute duration was precisely predicted from the orbital mechanics. They had prepared for it, they had drilled it, they had discussed what they would do, and Wiseman said in the debrief that the moment the signal dropped he was at the window and the crew gathered. Not necessarily at the same window, just together, in the shared space of the capsule, and that before the checklist started, before anyone reached for anything. There was a moment of acknowledgement. He could not fully describe the moment. He tried in the press conference and stopped. He said some experiences require a different kind of language, and that he had not found it yet. But he described what happened when the signal returned and Earth appeared over the lunar limb. He said the four of them were at the windows, and that for a moment, Mission Control waiting, Houston waiting. Nobody said anything on the radio. 4 people. at 250,000 miles from home, looking at a small blue circle at the edge of the moon, and nobody said anything. When they finally opened the radio channel, Wiseman was the first to speak. Mission Control confirmed that communications had been re-established. The post-blackout checklist began. The mission resumed its operational tempo, but that moment, the duration of it, the four of them looking at the Earth in silence at the greatest distance any of them would ever be from it, that moment is now part of the historical record of this mission. Here is where the investigation honestly stands. What is confirmed? Artemis II launched April 1st, 2026. The crew set the record for the farthest distance any human being has ever travelled from Earth, 252,760 miles. They conducted a planned communications blackout of approximately 40 minutes while behind the moon. They experienced a total solar eclipse from near the moon lasting approximately 1 hour, the first crude observation of a solar corona from that position in history. They observed multiple transient light events on the darkened lunar near side during totality. They photographed the Oriental Basin, portions of the South Pole Aitken Basin Rim, the Vavilov Crater, and other far-side features. They experienced Earthrise upon emerging from the blackout. They are returning to Earth on schedule for splashdown April 10th. What is in analysis? The transient flash observations from the eclipse period, pending comparison against the Neliota and Marshall programs' baseline datasets, and against impact flux models for the near-Earth environment. The photographic data from far-side features, captured at novel sun angles and phase geometries, pending processing and comparison with existing orbital datasets. The crew's psychological and physiological responses to the deep space environment, to be formally assessed in post-flight medical and psychological evaluations over the coming months. The heat shield behaviour during crewed re-entry from lunar distance, which will produce the most technically consequential data of the mission. What is not yet known? Whether the eclipse period flash observations reveal anything beyond the expected impact flux. Whether the Vavilov photometric data can discriminate between volcanic and impact melt origins for the crater floor. Whether the heat shield behaviour falls within the parameters predicted by NASA's corrected post-Artemis I models. These are gaps in the current state of analysis, not gaps in NASA's credibility. The mission concluded recently. The data is new, science is not instant. This is how it works. The Apollo missions returned hundreds of kilograms of lunar rock. Some of those samples took years to fully analyse. Some are being actively studied today 50 years later, because analytical techniques available in 2020 are more capable than those available in 1972. The sealed container of Apollo 17 soil collected in December 1972 was opened for the first time in 2019, specifically because the instruments available in 2019 could detect things that the instruments of 1972 could not. The science of Apollo is not finished. The science of Artemis II is just beginning. One more thing. The 40 minutes is not a dramatic device. It is a physical fact. And the thing about physical facts at that scale, at 250,000 miles, in a 40-minute silence, behind the far side of a world that humanity has been staring at for as long as there have been human eyes to stare, is that they produce experiences that resist translation. Wiseman said he had not found the language yet. He will, probably. Astronauts write books. They give lectures. They describe over decades of interviews, gradually refining the account, finding better words for things they experienced quickly and processed slowly. Edgar Mitchell walked on the moon in 1971 and spent the rest of his life, until his death in 2016, trying to communicate what he called the flash of understanding he had on the return journey. He was not a mystical person before the mission. He was a Navy captain, an MIT doctoral graduate in aeronautics and astronautics, a test pilot. And after the mission, he spent 40 years searching for language for something that happened to him in cislunar space. Wiseman has been home for a matter of days. He is in post-flight medical evaluation. He is debriefing mission controllers. He's doing what astronauts do immediately after they return. He will find the language, eventually. Some of it he has already found. Complete is a good word, a precise word for what he was describing. The rest of it will come with time. What the crew saw behind the moon is partially explained, partially an active analysis, and partially waiting for the kind of language that Wiseman described. The kind that requires not more words but more time. The planet looks the same from us 252,000 miles as it looked from 248,000 miles in 1970. Small, blue, alone in an enormous darkness, surrounded by nothing that is trying to help it, and worth choosing every time without exception. The investigation continues. Splashdown is April 10th. The analysis is ongoing. The crew is on their way home. We will return to this when there is more to report. When the flash analysis is published, when the photometric data from Vavilov is processed, when the heat shield data is confirmed, when Wiseman has found better words. Until then, this is what the data says. This is what the crew confirmed. This is real. This is not speculation. And the investigation has only just begun.